Hello, today we're going to talk about some chemical bonding and do a little review of the three types of bonds. You do have three types of bonds in chemistry, and again, these bonds are what causes atoms to bond together or glue together to form compounds. You've got your ionic bonds, which are between the metals and the nonmetals. Metals will give up electrons, making them cations. Nonmetals will tend to take electrons because they're closer to the noble gases in their configuration for electrons, so they'll tend to take them. And so there's a complete transfer. When you have, for example, in an ionic bond, when you have sodium and chlorine, sodium will completely give up that electron to chlorine because whenever he does that, chlorine has a full valence outer shell, and sodium doesn't want that electron because now he has a full outer shell. When he gives it up, he'll be more like neon. So in ionic bonds, you have a complete transfer of electrons. It's a very, very strong bond. They have high melting points. They're very, very bonded together very well. Covalent bonds are going to share electrons. These are nonmetals with nonmetals. Or if you have nonmetals and hydrogen, like ammonia, those kinds of things, or water, for example. Water has hydrogen and oxygen. That's a covalent bond. Now, in a covalent bond, you're going to have some sharing happening. So let's look at oxygen and oxygen, for example. This oxygen had 6 electrons, okay, of his. This oxygen also had 6 electrons of his. 1, 2, 3, 4, 5. 6, okay. But they have to share the electrons in order to have that full valence shell. So there's not a transfer because this oxygen is counting on all of these 4 shared electrons as well as his own 4. And this oxygen is counting on, again, those shared electrons plus his 4. So it's a weaker bond. They don't hold together as strong, so they have lower melting points. They don't conduct electricity very well. Then you've got polyatomic bonds. Polyatomics are generally between your metals and these ions that are on your chart. Now the polyatomic ions on the chart, these are covalently bonded groups. Okay, so these are sort of like your best friends at the lunch table. Those are the ones that you're really close. You share your secrets with each other, those kinds of things, and just spend more time together. So the polyatomic ions are covalently bonded themselves, but then they bond with a metal. So the bond between the metal and the polyatomic is an ionic type bond. There's actually a transfer of electrons. So it's sort of a combination of both. Just want to point out there is one cation on the polyatomic chart, ammonium, and so he can be in the metal position with that bond. Okay, let's keep going. Now, in a metal bond, these bonds can have several different oxidation states. So you don't know. If you have a group 1 element like lithium or beryllium or magnesium, you can look at the column and it tells you immediately their oxidation state. But when you have those D block elements, you don't know the oxidation state unless you're told. So for example, in lead can have several different oxidation states. So in order to know it, they'd have to tell you in the name. So if they said lead 2 oxide, 2 stands for the oxidation state. So you just write a +2. You get the oxygen from the group that it's on the periodic table. Oxygen is in group 6A. He only needs 2 more electrons to get his full valence shell. So you put them together, you crisscross just like we've learned in the past. This is an ionic type bond because you have a metal and a nonmetal. They would have 2 each, but you notice that if lead needs 2, or excuse me, is going to give 2, oxygen is going to take 2, you can just bond 1 of each together. That's the simplest form. Again, if they tell you about copper sulfide, you can't look at copper on the periodic table and tell his oxidation state. It has to be told. These are in Roman numerals, by the way. +1 would be his oxidation state. Sulfur from the periodic table needs 2 electrons, so she's going to take 2. She changed her name when she was bonded from sulfur to sulfide. So you crisscross, and you can write your formula. You need 2 coppers for every sulfur. Okay. If you're given the formula for a metallic compound, you need to write the charge. So you need to go backwards. You might be given the formula, you might be given the name. Now this 4 on the bottom of oxygen came from lead. This 2 on the bottom of lead came from oxygen. Now you have to go backwards here. So the oxidation state of lead before you made this compound was a +4. He gave away 4 electrons. But each oxygen took 2 electrons. Well, when you write the name, you don't care about the subscript. You're looking at the oxidation state. So I would have to write a 4. Lead 4 is the oxidation state. And oxygen changes to oxide. Copper chloride. Where did this 1 come from copper? The chlorine. Where did the 2 come from chloride? The copper. So if you go backwards, you can write out the oxidation states. Now you can write the name, copper 2 chloride. The 2 came from this 2, the oxidation states. Let's practice. Cobalt 3 chloride. Where did the 3 come from? Cobalt had an oxidation state of 3. Chlorine always has an oxidation state of -1. Okay, so when you crisscross, what do you get? Here you go. Good. Okay. Iron 2 oxide. The 2 was the oxidation state of iron, so it's Fe +2. Oxygen is -2. What do you notice about +2 and -2? You don't need to write Fe2O2. You can just simplify it to FeO. You just need one of each. Okay, lead 4 chloride. Again, the 4 is the oxidation state of lead, so you would write a +4 up here. Iodide has a -1, and when you crisscross, you get letter A. Let's try going backwards. If I give you the name, could you write the formula? Chromium, you're saying, from the word, has a +1 state. Sulfur from the periodic table needs 2 electrons in order to have a full valence shell. So when you crisscross, you get Cr2s. Copper has a +2 state from right here, oxidation state. Iodine has a -1. When you crisscross, you have copper with 2 eyes. I see you with 2 eyes. Okay, zinc has a +2 oxidation state. Sulfide has a -2. What do you notice about these? They're the same, so you can just write one of each. Lead has a +3, which you got from the name. Chlorine has a -1. When you crisscross, you get 1 lead and 3 chlorines. Let's double check. And there's our answers. Okay. Now you're looking for the name of this. Now again, you got to go backwards. This 4 came from up here, and this 2 came from over there. So first thing you got to do is figure out what is Mn. Is it magnesium or manganese? Well, it's magnesium. It's manganese. So the +4 came from manganese. So you need to pick one of the manganese. Again, it's a +4, so 4 is his oxidation state. They're not asking for the subscript. And there would be his answer. Chromium, the 3 came from chromium, so that's the number it's looking for, and the 2 came from sulfur, so the answer is C. Have this chart handy whenever you're doing the next little group of practice here. Okay, the formula for potassium carbonate. So potassium's a metal, so it's going to be a cation. Carbonate on your chart is going to be an anion because it's going to take those 2. This is covalently bonded, but when you add it with the metal, this metal and this polyatomic acts like an ionic bond. So it's sort of a combination here. Okay, so you're going to crisscross your charges. You need 2 potassiums for every carbonate. You do not need these parentheses here. It was there just for those purposes to show you. If you'll notice, each potassium has a +1 charge and the carbonate has a -2. Your total charges in your compound need to equal 0 to make a neutral compound in the end. Well, let's look at these. Ionic formulas with polyatomics. Again, they're going to act like a metal and a nonmetal. Ammonium is one of our few cations on the chart. it has a +1 charge. Sulfur has a -2, so you need to crisscross and drop. But when you do that, ammonium stays ammonium, but you need 2 of them, and you only need 1 sulfur. Aluminum has a +3 charge. When you look on your chart, nitrate has a -1 charge. So when you crisscross, okay, you only need 1 aluminum, but you need 3 nitrates. It's very similar to how you did ionics. It's just that instead of having 1, you actually have a little group now. Calcium has a +2 charge. It's in that second group. It's going to give up 2 electrons to be like argon. Carbonate, if you look on your chart, has -2. What do you notice about these 2 numbers? They're the same, so you just need 1 of each. You could crisscross and get 2 and 2 and then simplify, but if you notice they're equal, you can just have 1 of each. Potassium has a +1. Phosphate has a -3. When you put them together, you need 3 potassiums for every phosphate. Okay? Let's see the neat version. And those are also your names. You do need to name them. Okay, sodium hydroxide. Sodium is on the periodic table. Hydroxide is on your polyatomic chart. So when you look at those, you need to say that sodium is going to give up 1, it has a +1. Hydroxide has a -1. So you just need 1 of each. You crisscross and drop, and you get letter C. Mercury 2, mercury had a +2. Sulfate on your polyatomic chart has a -2. You just need 1 of each, 1 mercury for every 1 sulfate. The answer is C. Ammonium has a +1 charge. Sulfide has a -2 charge. You crisscross, you need 2 ammoniums for every 1 sulfide. The answer is A. Here we go. Now we're going to go from the name. Lead. All right, it tells you that lead has a +4 charge. Phosphate has a -3 charge. Okay, so when you do that, I don't think I put the 4 here. Okay, all right, you need 3 leads for every 4 phosphates. Aluminum on the periodic table has a +3 charge. It's not a polyatomic. Chlorate, ClO3, has a -1, so you can crisscross. You need 1 aluminum and you need 3 chlorates. Okay? All right. The correct name for calcium and then the OH. The OH came from the chart. You don't change the last name when it's a polyatomic. Keep the name that's on the chart. Calcium and hydroxide. You don't need any 2s. You don't need anything. This is not a transition metal bond. It's got a metal and a polyatomic. So you say the metal's name and you say the polyatomic's name. So the answer is A. Copper. How many carbonates are here? Just 1. The oxidation number goes up here. The 2 came from carbonate. So you do need the Roman numeral because you have a transition metal. And the D block are the ones underneath the metalloids. So you're looking for the oxidation state of copper. The oxidation state was 1, which came from up. Let's practice these. Lead and sulfate. You only needed 1 of each. Now this one's a little bit trickier because you know that sulfate has a -2. Okay, but there's only 1 of each. So it can't be lead 1 because you needed to transfer those 2 electrons. This is a simplified version. So this is actually lead 2 sulfate because you needed to balance the sulfate ion. Okay.